All right. So welcome back. We're now on part three of the second lecture. We are almost done. There's probably one more video after this. I guess we probably have to go to part four. Sadly. Um, so we've gone through quite a bit. We've almost finished this chapter two. Chapter two, lecture two. It's all about chemistry, and it's all about chemistry and how that affects water. So we talked before about water, um, and we said all these cool features of it. Water molecules stick together. Water moderates the temperature of the environment. When you sweat, it's gross, but it cools you down. And then we said water molecules or ice floats. So solid water is less dense than liquid water, so it actually floats. That's weird. Most solids are actually more dense and would sink in that same element's liquid. Then we said solvents are versatile. Water is the solvent of life. There's something known as a solute and a solvent. A solute is the smaller amount you add to a solvent, which is often liquid. You mix them together and you get a solution. It doesn't have to be as easy as just solid and liquid. It might be something like this here, which is carbonation, carbon dioxide bubbles in a liquid. We said this is the most important thing I think we've talked about maybe so far. These terms that are going to keep coming up over and over again. Hydrophilic substances love water. They dissolve in water, like salts and polar charged molecules. And then hydrophobic substances are afraid of water. That includes non-polar substances like fats, lipids, and oils. They don't dissolve in water. They separate. They're immiscible, so they form something like this, like we said. The poor man's lava lamp, right? And this is an example of a hydrophilic substance, salt, that mixes and forms a solution. Then we said there's acids and bases. Acids, an example of that would be hydrochloric acid. An example of a base would be sodium hydroxide. We said you can measure the acidity and basicity based off the pH scale, which is this nice scale from 0 to 14. It's generally that, but it can be a negative number or above 14, but often we call it 0 to 14. If you're below 7, if you're under 7, less than 7, then that means you're acidic, like coffee and stomach acid and soda. If you're above 7, you're basic, like bleach and like ammonia and seawater and stuff. We said the most biological fluids, most fluids of humans and of living organisms, most of them try to stay near 7. So the pH of the blood is 7.4. It's basic because it's above 7. pH of the urine is acidic. We say that because it's below 7. So we use these really important terms here, and I suggest you commit this slide to memory. A lot of people get confused with this because of the terminology. It's really confusing, and I get it, but you want to make sure you go over it and go over it and go over it. An acid has a pH of less than 7. We call that a low pH. Bases have a pH above 7. We call that a high pH. Acids have high levels of hydrogen ions, a high concentration. Bases don't, they have low levels. As a result, they have high levels of hydroxide, OH. So all these terms could mean base. All of these things can mean acid. So it's really important to use that because these are often used interchangeably. And we said there's a lot of OHs here. That means that's a basic solution. There's an equal number of OHs and H's. That means it's a neutral solution, has a pH of 7. There's more H's here, a high concentration of hydrogen ions. That means it's an acidic solution. Now, here's the new part that we're getting to now. Most living things, like we said, try to stay close to 7. The pH of the blood is 7.4. Urine is a little, acidic. But we want to keep our blood, the main fluid inside of us, near 7. If it changes, then that's bad. Because, like we said before, some of you want to change your blood pH. You want to acidify it. You want to, alkaline your blood. Don't do that. You want to keep it what it is and don't change. If you do start changing it, You're going to start hyperventilating. You're going to, decrease. You're going to start hypoventilating. You might throw up. You might start having diarrhea because your body's trying to say, let's fix these levels. We got to fix these levels. So to keep these levels as close as we can to what they need to be, we use something called a buffer. A buffer is a chemical that resists a change in pH. That's a really important point. It resists the change in pH. So if you have a buffer, so sometimes there might be a buffer, let's say in human blood, it tries to keep the pH at 7.4. If you add acid, the pH is going to go lower. It becomes 7.3, 7.2, 7.1, 7, 6.9, 6.8. But if you have a buffer, it's going to say, I'm going to try to not allow the pH to change. If I add an acid, I'm going to try to keep it at the same level by, taking in these acid, H's, the hydrogen ions. If I start adding bases, I'm going to try to keep it at this level, not let it go to 7.5, 7.6, 7.7, 7.8. I'm going to release some hydrogen ions to try to keep the pH from changing. That's a really important point. Buffers resist changes in pH. So if you add an acid to a buffer, here's an example of a buffer. If you add an acid to the buffer is going to say, I need to keep the pH the same. So if you added an acid to the solution, it's not going to let the solution get acidic. It's going to try to stop that. So to do that, it's going to bind this. The acid release this because acids increase these levels. The buffer is going to say, let me grab that and turn into this. The pH of the solution doesn't change because this is bound and it's pretty much hidden, so it can't affect the change of the pH. Now say some buffers exist as this. You add a base to a buffer, and it's going to say bases decrease the levels of hydrogen ions. So it's going to say if you start adding bases, which is taking these away, the buffer's going to say, I know what to do. Since you're adding a base, I can't let the pH get basic and start going up. I need to lower it by releasing this. That way I can keep that pH the same. That sounds a bit confusing. It's because you might not know a lot about pH yet because you haven't reviewed those slides. But remember, buffers try to resist changes in pH. It tries to keep it at one level depending on the buffer. There's a buffer that tries to keep it at 8. There's a buffer that tries to keep it at 4 and it wants to keep it there. If you add acids or bases, it either adds hydrogen ions or takes them away to keep those levels from out changing. So let's just do a quick practice problem to hopefully kind of demonstrate what we know. So Jonathan, good old Jonathan, adds some hydrochloric acid to a bowl of water. What happens to that pH? Do you think that pH is going to go down or going to go up? So if you add an acid to a bowl of water, let's say that water is about pH 7. If you add an acid, what's going to happen? Acids lower the pH. So the pH is going to go down. Is that solution now more acidic or more basic? Well, you think if you added an acid, and now you have a lower pH, it's going to be more acidic. Now, good old Jonathan here does something a little different this time. He adds some hydrochloric acid to a bowl of buffer. What's going to happen to the pH? Well, you're adding an acid. You would think the pH is going to go down. That's not the case because it's a buffer. You have to go back to what buffers mean. What does it mean to be a buffer? A buffer resists the change in pH. So if he adds it to a buffer, what's going to happen to the pH? The pH should not change much at all, if it does even change at all. Why? Because buffers resist the change in pH. If you add an acid, it's going to take in these acid components to pretend they're not there. If you add a base, it's going to release some acid components to kind of neutralize it. So like we said in review, that's the end of acids and bases now. Now we're about to finish up with water. But like we said in review, water is really special. It has these 4 emergent properties that make it the solvent, the liquid of life. You have all these properties. Water molecules stick together because of cohesion. Because Water molecules are polar and they have hydrogen bonding. So there's cohesion, where water molecules stick together and they form those dewdrops and all that. Water moderates the temperature of the environment. When it's hot outside, it takes in heat. When it's cold outside, it releases heat. That's why things like the Weeki Wachee River, those the Weeki Wachee Springs, why is it that it's cold? It's at 68 degrees, whatever temperature it is, all the time. Whether it's really, really sunny outside or whether it's really, really cold outside, why does that water not change much in temperature? Most big bodies of water don't, because water resists changes in temperature. It takes a lot of heat and a lot of heat only causes a small change in temperature. And that's one of the reasons, like we said, how deserts get so hot and so cold, because there's no water to regulate the temperature of the environment. Water also regulates the temperature of your body because of sweating, like we said. We said ice floats in liquid water because ice is more organized, so it floats. Good thing it does, or else we'd all die, like we said. Then we said it's a versatile solvent. Hydrophilic substances dissolve in it. Charged ions or polar molecules like salts, or hydrophobic molecules don't dissolve in it. They're immiscible. They don't mix well, like oils, fats, and liquids. And then we talked about how water is about pH 7, it's neutral, and then is a good solution for acids and bases. And then we said a water-based solution is called an aqueous solution. So we talk about water and all these things. That is why when we try to find life on other planets, we say, could there ever be life on Mars? We look and we say, I don't know. Let's go examine the planet, and we try to look for water. Why? Because water is the solvent of life. We found some planets outside of our solar system, and some have water. So let's say, the aliens, it's Independence Day and the aliens come attacking. Well, that's okay. Let's just get, some ships, and then we'll leave and we'll go, live on another planet. Although that really won't work as well as we think. There's lots of other factors. But we try to find other planets. We look for signs of life, and maybe in case our world ever gets destroyed because people are polluting and global warming and yada, 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 we want to find somewhere to go. We want to see, hey, where are the aliens at? Where are they at? So we look for water for that. And in fact, cool news, they actually found that Mars has water on it. So here's just the kind of picture. They found some frozen ice, I believe, on water, and they also found kind of remnants of what they could prove to be almost like flowing water went through this area. So now we just have a couple of practice problems, and then we're going to end the portion on chemistry and water, and then we're going to move on to lecture 3, which is based on the organic molecules of life. So what is this entire structure called? This whole thing here. It's an atom. What's this thing in the center known as? That's the atomic nucleus, right? What two things are found there? The pink and the brown things, what are these? What subatomic particles? Well, protons and neutrons are found in the nucleus. But remind me of their charges again? Protons are, they're positive, and neutrons are neutral. What's this structure known as? This little yellow jelly bean. Is it earwax jelly bean? What is that? By the way, don't ever try the earwax ones. Those are nasty. But what is it? It's an electron. What's its charge? It's negative, right? Whoop. And what's this thing known as? This little yellow beam, or all these electrons would be. We call that the electron cloud. So now another practice problem. What the heck is this thing here, this 2? What do we call this value? That's known as the atomic number. What does it tell you, though? It tells you that this element, helium, has 2 protons. The atomic number 2 tells you this element has 2 protons. All elements on a periodic table have a neutral charge. That means helium is 2 protons. How many electrons does it have? 2, because it's 2 positive and 2 negative charges because it's neutral. What is this value down here known as? That's the atomic mass, right? What does it tell you? It tells you the total number of protons and neutrons, right? So this helium has 4 total protons and neutrons. So let's do another practice problem. Right here is cadmium. How many protons in there are based off this information? How many protons? 48, right? How many neutrons? Some of you are like, 48 because it's electrically neutral. Now don't say that. Remember, this number down here is the atomic mass. It tells you how many protons and neutrons. If there's 48 protons, how do you calculate the number of neutrons? Right, so you got to subtract. So you do 112.4, so let's just say 112 minus 48. And then you get a number, right? So I think 64. So yeah, I think it's 64. I don't have a piece of paper to look at it, but I'm not very good at math. But anyways, so let's just say 64. So you just do the subtraction problem, and that should be right. So how many electrons are in cadmium atom? Like the one that's listed on the periodic table. 48, because they have a total number of, it says 48 protons, it's neutral, so there should be 48 electrons. Here you have these things here. CHON. Carbon, hydrogen, oxygen, nitrogen. CHON. What's special about these 4 elements? I've heard of these before. These are the ones, the primary things found in tobacco which kill you? Isn't that what we said? What did we say? What's special about CHON? These are the elements of life. They're essential elements. They're required, and they're the most abundant elements in living life. They're about, I think, 96% of all living matter is made up of CHON. 96% of your pet dog Fido. 96% of your goldfish Kiki. 96% of you is made up of these. And a lot of you, you say, well, you don't know me. I just drink so much milk. I must be a lot of calcium. I bet you think you are. You're not. You're still 96% of this. Some of you, I'm really, 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 really manly. I grew my first chest hair when I was like 5. I bet you did. Doesn't matter. You're still 96% CHON. Just like girls, just like dogs, just like cats, just like parrots. We're all the same. 96% of these elements. So nitrogen here has 7 electrons. How many protons does it have? If it has 7 electrons, it has 7 protons, right? Because it's electrically neutral. And you look at this. This is just an extra question that I think would be kind of cool here. How many valence electrons does nitrogen have? You don't have to remember it. You just got to look at this picture. How many valence electrons? Some of you are thinking, well, 7. He told me there's 7 electrons. There's 7 valence electrons. No. Remember, valence electrons are the outer shell. So there's 1, 2, 3, 4, 5. So nitrogen here has 5 valence electrons. A neutral nitrogen has 5 valence electrons. Here, you got this dew, sticking on the grass blades. Sucks when you get them on your new Jordans, right? But what's this property of water known as that causes water to stick together? What's that known as? Cohesion, right? What about this? How can water support this, tarantula or this pond skater? Why did Jesus lizards walk on water? How can they do that? What's this property known as? Cohesion causes the water molecules to stick together. I think this is a really good example of surface tension. That's why you can jump and do a backflop and then get, a really bad bruise on your back, because water has this tension on its surface. It almost acts like a solid, almost like a hard surface. So then you got this nice cup of water and you flick in a ice cube. Where will water end up? after being placed in water? It looks like it's going down, but where is it going to go after you wait, 2 seconds and you kind of see where the water's ended up? Does it float or does it sink? Solid ice or solid water floats in liquid water. Now you look at this. Another question. Which one of these is the solvent and which one of these is the solute? So these white crystal meth snowflakes. These white snowflakes, what are they here? Are they the solvent or the solute? They're the solute because they're in the smaller amount, which makes this blue, this water here, the solvent because it's in a bigger amount. Then there's Pepsi. There's bubbles. And there's liquid. Which one is the solute? The bubbles would be the solute. In this case, they're a gas. And the solvent would be the liquid. So here, oil doesn't mix with water. Because of that, here's the oil here. Oil doesn't mix with water. We call it what? We call it Is it hydrophobic or hydrophilic? Right, it's hydrophobic. Oil has a fear of water, so it doesn't mix. Salt, though, this is salt water, does mix with water. Salt does mix with water because it's charged. So salt, it's not hydrophobic, it's hydrophilic. It likes water. So now, classify the 3 solutions as acidic, basic, neutral, and explain why. So this one here, is this an acid or a base? It's a base. How do you know, though? Because there's not many hydrogen ions, and there's a lot of hydroxide ions. What about this one here? Is it an acid or base, or is it neutral? And why? It's neutral because there's an equal amount of hydrogen and hydroxide ions. And this one, it's acidic, right? But why? Because there's a lot of hydrogen ions in that solution. So which solution has a high pH? Which one? So this solution here has a high concentration of hydrogen ions. Does it have a high pH or a low pH? This one here. It actually has a low pH. That's weird, but remember on that slide I told you things are used interchangeably. So this has a low pH, and the basic solution has a high pH. And this one here in the middle, the neutral pH, what's its pH number? So give a number. Usually it's run from 0 to 14. Remember, what pH do you think a neutral solution is? 7, right. Okay, so now we're on chapter 3, lecture 3, where we're going to talk about the different molecules of life. Ooh, my Amazon Echo just started talking to me. So chapter 3, now, molecules of life. So, living organisms, they're mostly made out of carbon-based compounds, right? We talked about that. We said CHON. 96% of living organisms are CHON. Carbon, hydrogen, oxygen, and nitrogen. Carbon's really special, though. Carbon's really unique. Carbon is one of the most important things. Look at this here. It's the backbone of life. Why? Because carbon, of the way its valence electrons are, we're going to look at it, it can form really big, really complex, and lots of different types of molecules. In fact, fats, proteins, carbs, and DNA, they're all composed of carbon-based compounds. How interesting is that? Well, that's because all these things make up us. So here's a really cool picture of carbon. Carbon is this black atom in the center, bonding to a bunch of different things. Carbon can bond to 4 other atoms or 4 different groups, making a large variety, because then this can bond to something else. So carbon is the backbone of life. Most living things are made of carbon because of this property. So we get to something called organic compounds. So organic, I say this, and a lot of you are like, tuning me out already. You're already on Facebook, looking at all the news, seeing those new pictures of Lumiere and for the Beauty and the Beast. You want to see all that, and you're seeing what's going on with the weather, and I get it. But organic compounds is actually not what you think. A lot of you think you know what organic is. Oh, here's an organic one. Here's one with all the pesticides. You don't need to talk to me and lecture me about organic foods. I shop at Whole Foods. I know what organic things are. They start with that 9 with those produce digits. I know all about that. This isn't what we're talking about. That deals with pesticides. That's something completely different. Both of these here sprayed with insect, killers, and this isn't. Regardless, they still are both organic compounds. Because what organic means is, it's a class of compounds or molecules that are made of carbon. So if you're organic, that means they're made of carbon. Humans are organic. Chairs are organic. Glass is organic. These different things are organic, right? Because they're made up of carbon. Most organic compounds contain hydrogen in addition to that carbon. So a lot of times they're carbon and hydrogen. I like to think of those two words together when you think of organic. So carbon can form tons of different things. It can bind to 4 different other atoms because of its electron configuration. That determines how it can interact. Because remember, carbon has 4 valence electrons. That's really important. So how many valence electrons, try to go back and remember, without looking, how many valence electrons does an atom try to usually get? What's that rule? Is it the pentuplet rule? Try to get 5 kids, and once you're there, that's a good number. Some of you say, I can't deal with more than just one. Some of you don't have any. That's okay. But how many electrons, right, does carbon in pretty much most elements try to reach? How many valence electrons? 8, right. So carbon has 4. So there's a lot of different ways it could get to 8, right? It can form 4 covalent bonds where it shares and accepts, kind of shares 1 electron from a different atom. So they can form really large complex molecules because it could do that. Or it could just share, get 2 from one thing and 2 from another. So that's why carbon frequently mixes and matches and forms these CHON, carbon, hydrogen, oxygen, nitrogen, in living molecules, right? So here you can see, here they all are, CHON. Here's carbon, has a valence of 4. It can interact with these because these also want to get 8, so it can do it in a bunch of different ways. So carbon could partner with 2 oxygens, and that forms carbon dioxide, which is the gas you breathe out, which is the gas that's in your, Mountain Dew, right? Or ethanol. So carbon can then form with hydrogen here. It shares 1 electron with hydrogen, 1 with hydrogen here, and 1 with this carbon, and 1 with this oxygen. It can do that. It can form something called ethanol. Who here, knows anything about ethanol? Right? You heard of it. You said some things. Who here likes ethanol? Who likes to drink ethanol? A lot of you are like, ooh, that doesn't sound good. I think I heard that's in my gas, right? Let me rephrase this. Who here likes tequila, right? Now we're talking. All of you are, raising your hands. I have all of my hands up and all my fingers, and I'm waving them around. Love tequila, right? Maybe some of you don't like tequila. What about wine coolers? Yeah, ethanol in there too. So ethanol is one of the alcohols. It makes up alcohol, and it's that reason you feel really good, right? Whenever you drink it, and you get a little, little fuzzy, right? Because ethanol. So a lot of people like ethanol, right? Ethanol is great. So now we're going to look at something called hydrocarbons. So hydrocarbons are organic molecules that are made of mostly, like 99, a huge percentage of it's carbon and hydrogen. Carbon and hydrogen. Most organic compounds, like fats and lipids and all that stuff, they have hydrocarbon components. Proteins, they like to have hydrocarbon components, and so forth. So these hydrocarbons are really important because we can do chemical reactions with them. And this is the best part. they release lots and lots and lots of energy, like petroleum and octane. Anybody know what petroleum is? Right. So it's a hydrocarbon that's in gas. So petroleum is a hydrocarbon in gas. If you go to the UK, they always call it, petrol. You know, that's, instead of saying gas station, they get some petrol, and that's okay. And then octane. And anybody heard of octane? Right. So octane is actually a part of gas. Some of you don't believe me. And then you see these things and you look, minimum octane rating. So octane, it's a hydrocarbon that's in gas. You don't want to drink this one. It gives energy. So some of you are like, oh, drink it, now I can run my marathon. No, don't do that. Right. So I guess you're stuck with these. What the heck is this? Burnt ribs? Oh, well, right. But in dietary fat, these are made up of hydrocarbons. That stuff that we love. We love our oils and fats, all over our French fries and everything, goody goody, right? But those are hydrocarbons, and you eat them and you get lots of energy. The thing is, though, most of you don't go run marathons right after, so all the energy gets stored, and you get a tummy, right? You get a big stomach, and then you wonder why, and then you eat more because how delicious they are. Then you want to get skinny, like I do, right? But then there's pizza, and then there's French fries and ice cream. That ain't happening, right? So I think this is a good point to stop, and then we'll pick it up next time. So this is going to be the end of part 3 of the lecture. We talked about some really awesome things. We finished and we did some practice questions about the about chemistry, and then we got a little bit into these different organic molecules of life: carbon, hydrogen, oxygen, nitrogen, mostly focused on carbon, organic compounds, right? And then we talked about the different things and how hydrocarbons provide energy, and why carbon can do what it does because it has 4 valence electrons, right? Okay, so we'll pick it up off next time, and we'll have the final part 4. Hopefully that's the final part, and then we're all finished. So we missed everything, Thanks a lot, Hurricane Hermine.